Hello. So let's talk about Bohr and his discovery and his model of the atom. Up until Bohr, or before Bohr, when Rutherford discovered that an atom was a nucleus, which was a positive charge, and that atoms were mostly empty space, and that's where the electrons lived, well, then the race was on. Well, where and how do those electrons exist in that cloud? What is their nature? And in order to understand this, of course, you have to know a little bit about the electromagnetic spectrum, and that electromagnetic spectrum, those electromagnetic waves are really energy waves, and the higher the frequency, the higher the energy of the wave, the lower the frequency, the lower the energy of the wave. And invisible light, that would mean that red light is your least energetic, and purple or violet light would be your most energetic waves that you can see. Now, of course, there are many other energy waves that we cannot see. We need other ways to detect them. Well, back in 1911, they knew of other waves that could detect waves, but of course, visible light was the easiest. And so here in this box is a sample, or in this tube, is a sample of hydrogen gas. So it's clear and colorless. That gas in there, it's trapped. There's nothing but hydrogen gas in this tube. And you'll notice the two ends are metal. And what we do is put that into this box, puts a lot of voltage through, and gives a lot of energy to this hydrogen gas. So this is what we call the ground state of hydrogen. It's just at everyday temperature and conditions. And then we get it to what we call the excited state, because we give hydrogen lots of energy by throwing a bunch of electricity through it. Now, you don't have to throw electricity through it. You can heat it or burn it. It's also giving it energy. But the result would be the same. You would get a glow from the bulb or the flame if you were burning hydrogen, and have that like purpley kind of pinkish glow. Now, when I turn the energy off, of course, you go back down to ground state. And the color of the light tells us a lot about what's going on, because it's not the overall color itself, but it's what we do when we take a prism and look at the individual colors that are happening, right? Because white light is all the colors of the rainbow, Roy G. Biv. But this is not Roy G. Biv, it's a pinkish purpley color. So I need a prism to break it down to see, well, what kind of light is actually being shown to me? And if I do that and use one of these little gratings, it's like a prism, and put it over the lens of the camera. I'm gonna turn around here, hold on, I'm gonna mess that up. We should see some lines form from the bulb. And you'll see very clearly there's a turquoise line, there's a red line, and if you can see very closely, there's a purple line hidden back there. Now, of course, I'm rotating this a little bit to try to get as many of the other lines. Now, and those sets of lines repeat kind of in a starburst pattern, so I see it, several different angles. But you can definitely see in there, if I freeze it, there's some turquoise line or red line, and closer to the bulb, you might see that kind of purpley line. Now, because you're seeing those very crisp lines of light, that means that particular light has a very particular wavelength, or frequency actually. Well, wavelength and frequency, but we're going to focus on frequency. So that red line is one frequency of light, and it happens to appear to human beings as being red. That turquoise line is one frequency of light. And that purple line is one frequency of light. They call this the line spectrum of the element. And that's telling us a lot. Because remember, each little line or sliver of light is really saying, hey, this is a particular electromagnetic wave. It's a particular energy. And when Bohr noticed this, he put some things together, and it's really complex. So I'm really going to oversimplify things here. So does the book. If you really want to get into the study of this later in life, you can. I hope I don't oversimplify it so much that we just lose the entire meaning of Bohr and his experiment. But here's kind of what's happening. Bohr said, hey, look, let's have the electrons be in their everyday state. We call this the ground state. And for hydrogen, it's the easiest atom to look at, because if you're looking at the nature of electrons, well, hydrogen only has one electron. So you're only looking at one particular electron, rather than in other elements, a whole bunch of electrons. And what happens, what Bohr thought happened, which pretty much, nailed the beginning of our understanding of electrons and how they behave, is that, well, when I give this electron energy, when I add energy, I get the electron excited. So I give energy to this atom, and it's absorbed basically by the electron. The electron gets excited, and it jumps to what was discovered to be other energy levels. And energy levels are denoted by N a lot of the times. And so this particular electron got a shot of energy. It's like gulping down an energy drink. By the way, don't do that. They're pretty awful for you. But got energy and was like, woohoo! And then took off to what we call an excited state. And that doesn't have to be the next excited state. It can jump up a couple excited states. So this electron said, woo! And went up to here. The third energy level. And then, after a while, that electron's going to get tired, if you could personify an electron, and it's going to come back down. But the thing with energy is, in the way the universe works, energy cannot be created nor destroyed. So that electron took the energy, went up to the level, and then that electron decided to get tired and come back down. But when it gets tired and comes back down, it has to give back that energy to the universe. It doesn't have to give it back in the same way. We use electricity to get our electron excited, but when the electron comes back down, it doesn't give it back, doesn't give that energy back as electricity. It gave it back as light. And this is why one of those slivers of light you saw was red. And maybe the electron on another dance, if you will, gets excited. Maybe that electron, instead of going from here to here, maybe that electron goes from here and goes to a higher energy level. Maybe it goes up to n equals 4 or n equals 5. And when it does that, and then the electron jumps back down, well, because it went to a higher energy level and came back down, it's going to give us another color, probably more energy. Probably that either turquoise or that purple, because you're getting over more higher frequency with those colors. But here's the thing. Because hydrogens all have one electron, and when hydrogens, because they're all the same electron cloud and get the same amount of energy, all samples of hydrogen are always going to give us that same pattern of lines, because those electrons are going to do the same dance and get us back that same amount of energy. So Niels Bohr ran with that. He said, okay, that means that when electrons receive extra energy, they're going to dance in a very particular pattern at very particular energy levels for that particular atom. And that means those electrons must exist already at specific energy levels, let alone get excited to other very specific energy levels. And, of course, those patterns of those line spectra, spectrum is plural of spectra, those line spectra of elements, or the line spectrum of a particular element, is always the same for that element, meaning hydrogen's always going to have the same pattern of lines. Krypton is always going to have the same pattern of lines. Mercury is always going to have the same pattern of lines. And then, therefore, those patterns of lines, because they represent the energy levels of that atom, are like fingerprints. And so we can utilize those line spectral patterns to identify unknown elements. We can even aim our telescopes up at stars very distant away, get that light to filter through a computer, break it apart through a prism, identify the patterns, and we can tell what elements are contained in that star. Even could be, hundreds of thousands of or millions of light years away. It's pretty incredible. So, I know that's really weird, but the important points of the story. Bohr, excited electrons. Those electrons got excited and went up energy levels. When those electrons came back down to ground state, that atom always gave off the same pattern of energy back in the form of a very specific set of spectral lines. And those spectral lines, number one, tell us that those atoms live at very particular and travel to very particular energy levels. And number two, those sets of lines, spectral lines, a line spectrum, is like a fingerprint for particular elements. Each element has its own pattern of lines. Okay? All right, I know it's weird, but try to process it. Thanks. I forgot to make mention. I'm going to take a couple minutes and I'm going to show you some hydrogen again, but more in the dark, so you can see that pattern of lines. And I'm going to show you some other elements and their specific line spectral patterns of lines. So it's just kind of cool to see them in action, if you will. All right, so enjoy. Thanks.